Did I accept it?
I did.
Oh, you did?
I did.
Okay, great. All right, welcome everyone. So it's a pleasure today to have Vivek Singh from us here from CQTS, who is going to tell us about Chern-Simons theory, not polynomials and Quivers. Vivek, please.
Thank you so much. So today I'm going to talk about the unexpected relationship between the quantum theory and the mathematical theory of knots. So which is basically knot theory is like Chern-Simons theories play a natural framework to study the knot, and yeah. So based on my work, yeah. So I will briefly discuss the work with collaboration with Ramadevi, my supervisor, and the Indo-Russian team, and Satoshi Nawada. So plan of my talk is first I will give the brief introduction, what is knot theory and its connection to the Chern-Simons quantum field theory. And then I will briefly discuss the mutant knot, which is it's a claim that the mutant knot cannot be studied in the Chern-Simons theory framework. But in 2014, we gave the formal description why mutation can detect within the Chern-Simons framework. And then I will discuss with the Vivek knot. So it's a infinite class of hyperbolic knots, which is recently it's so a lot of attraction from the math and physics both sides. So I will discuss the brief, and then there are ongoing recent development in knot-Quivers correspondence. So I will give just a brief introduction to what is knot and Quivers correspondence. So at the end, I will give the brief summary and discuss open flow. So what is knot? So knot is basically is a closed curve, closed-oriented curve, and which preserve under any continuous deformation. So continuous deformation means here it's you can stretch, you can twist, you can bend. It does not deform. It's a stable object. And link is made up of more than two or three more than two component knots. So they are linked with each other. So that's a rough definition of the knot and link. And this object is defined in three-dimensional space. So it means if you go in the higher dimension, you have some choice of allowed moves. You can perform like doing over to under. You can unknot this. So this object is well defined in three-dimensional space. So it has some sense if you are living three dimensions. So and here is the so around mid of 19th century, Lord Kelvin has some crazy idea. He thought that the knot is nothing but it's like it's a vortex of atom in an ether medium, and his then he thought that if he's right, then let's make a periodic table of knot. So how do we classify this periodic table of elements, like giving the atomic number and atomic weight? The same way here, one can he made the periodic table of knots. So giving the crossing number is like the classification of knot. So it's 3 means it's like a 3 crossing knot, and 1 is like there exists how many number of distinct knot in 3 crossing. So in 3 crossing we have only 1. If you go in higher crossing, you can see like in 6 crossing there are 3 distinct knot, topologically distinct. I will explain what is the meaning. So and so on. So when we go on the higher crossing knot, this number grows exponentially. So the chemists ruled out this idea. So this is not, we cannot map the periodic table of elements. So now this is the main challenging problem in the math. How do we distinguish these two knots if suppose they are same crossing? So there are a set of moves described. It's called red muster move. And if you go from one knot to other knot, it is then it is same knot. Otherwise, it's a distinct knot. And of course, this is very challenging task to do. And like if I can give you any complicated knot and you can say which knot is this in the table. So this is a very challenging problem. Then further, like this development, they associate, they tag the polynomial. Suppose if a given a knot, you can compute the polynomial, and if they share a distinct polynomial, they are distinct knot, and if they are the same, so so this is the development. So suppose we need to define a strong topological invariant quantity which satisfy all the allowed moves. And so this is the famous polynomial is called a Jones polynomial. There are so they describe by a set of scheme moves. So you can perform any crossing, focus on one crossing, and there are three independent moves. They are related by this scheme relation. And so these things also, there are application in the biology. There are certain agents, they do this kind of operation in our body. So how do we compute this polynomial? So let's start with the trivial. Suppose if you have a loop and then you have twisted. So it's just a unknot. And also, yeah, the Jones assume that the trivial loop, I mean we call it unknot, is 1. Its normalization is 1. So if you like, this is the Millennium Prize problem. If you suppose if you compute any trivial knot and whose Jones polynomial is 1, so this scheme relation failed. So till now we don't have any such example that whose any trivial knot whose Jones is 1. So you can start with some trivial knot, and then you can go for higher crossing knot and follow the scheme relation. You can compute this polynomial. But we know this polynomial is not powerful, because as example you can see that there are a set of examples. So 5, 1 and 10, 1, 132. So 5, 1 is a 5 crossing knot, and 10, 132 is a 10 crossing knot. They are topologically distinct, even a crossing number you can see. But if you compute the Jones polynomial, you get a same. So it's not powerful. Then there are like the refined, like the improve further home PPT polynomial. So it is 2 variable, and this is also not powerful because there are still lots of example exist which say a same home PPT polynomial. But the yeah, so there are a couple of example. I can show you that they share even the knot is distinct, but they share the same home PPT. So there are further improvement that's called Pohono polynomial. That is more power. So that is more powerful invariant. And this is the status in the math side. Then again in 1889, so in 1989. So and other question you can ask, what is the meaning of this variable? So so this is connection come again in physics side. So the base theory we can deal, because this knot lives in the 3-dimensional space, and it's a topological object because the size and shape does not matter. So base theory is a Chern-Simons theory and defined on S3, and the physical observable is a Wilson loop operator. So if you compute the expectation value of this observable and put the representation is a fundamental, you will get this well-known knot polynomial. So if you choose the gauge group as a SU2, you will get a Jones polynomial, and SUN then it's a home PPT. If you put the SON, you will get a Kaufman polynomial. So now here is the ocean of this invariant, because here the representation is, we can put any representation. So suppose if any 2 knot, it cannot be distinguished by, let's say, fundamental or it's a home PPT. You can put a color, the higher rank dimensional representation, and they be distinguished. So of course, so this is more powerful, and it's So let me briefly discuss this Chern-Simons. So Chern-Simons action is defined on the S3, and so if you compute the partition function, that depend upon this K is a label and A is a gauge connection. So the partition function is only depend upon the label, and the physical constant is a K is an integer because of the theory must be a gauge invariant. So here K is an integer. And if you put a source is called a Wilson loop, and the physical meaning of this, it carries the any one degree of freedom. So basically, not invariant is nothing but we are computing the amplitude of any one. So that's how the physical interpretation in the. So yeah, and here is the Wilson loop operator, and if you compute the expectation value of this operator, you will get a not invariant. So this is a formal construction. But here we can compute the exact polynomial. So there are several methods. So this is the example where q is an exponential to root of unity, and a is a q to the power n. So that's the interpretation, physical interpretation of this polynomial. So in this Chern-Simons framework. So here is a Chern-Simons invariant can classify the knot. The classification problem at least, because suppose if two not is say the same polynomial, you can go at a higher dimensional representation and they do distinct this. So yeah, so here we have a couple of methods which I am familiar with this Chern-Simons theory, and there is surprising connection with the two-dimensional theory. So it's like ADS-CFT. One can perform the 3D computation from low-dimensional theory. And then highest bit method and vertex model. These are the method one can compute and then not invariant. And the exact invariant I am talking about. And the polynomial form is, you can say there is a two variable and the coefficient is always integer. This is for a knot. A link, it can be somewhere a denominator. It's not actually exact Lorentz polynomial form, but for a knot, it is always be a Lorentz polynomial. So yeah, so can we compute the exact computation in this framework? So so we can do. So there is a work, the direct computation work by Cole and PRG and my supervisor Ramadevi. So they did the exact computation, use these two ideas. So one is if you do the Chern-Simons path integral on three-dimensional manifold, which has a boundary, let's say any oriented Riemann surface, and Wilson line gives the puncture on the boundary. So there is a connection with the, this is a Witten work. So there is a connection from the two-dimensional theory, and where this gives a vector state on the two-dimensional theory, whose basis are n-point conformal blocks of GK, this conformal model. So where K is a label of the Chern-Simons label. So using one this idea, and other is any knot can be redrawn as a closure of a braid. So here all the knot which you saw in the table, one can redraw as a closure of braid, but this is called a quasi-plateau. It's not exactly closure. So you have to cap this to get this. One can do. There are lots of all. This is the I think Artin or Alexander theorem that any knot can be redrawn as a closure of braid group. So these two ideas they have included. And now how do we do this computation, exact computation? Take a three manifold. This is S3, and you have a knot. You can chop it this manifold into many pieces, and this locally look like a sigma. Sigma is a two-dimensional Riemann-oriented surface, and you have sigma cross R, and do the computation and fit it, glue back. So gluing is like nothing but this. This two are opposite oriented boundaries. So gluing this two manifold is like you will get some vector state here in two-dimensional space, and gluing is nothing but is doing the inner product of vector. So you will get the exact Chern-Simons invariant. So this is the direct computation. And here one can look the physical picture, because Chern-Simons theory, if you compute the energy tensor, so it is 0. So the Atiyah axiom said that you can have a transition from vacuum to vacuum. So there is non-trivial transition. So basically these are the anions. You can drag from the vacuum and do all kind of this topological quantum computation in the middle part. So there are lots of work in this direction. So now, so this class, so we are basically looking any knot which we can redraw as a closure of 4-strand grid. This is this because we want to compute the exact computation. So that's why we classified any knot as a closure of 4-strand grid. So basically, we can divide into knot into two pieces, either knot belonging into 4-point conformal block or more than 4. So more than 4 we call non-arborescent knot, and if we can draw as a 4-puncture boundary, so it's called arborescent knot. So any arborescent knot we can compute Chern-Simons invariant for any integrable representation. So that's why our technique to evaluate this polynomial. So yeah, here's the CFT data. So in the 4-point conformal block, we have two equivalent bases exist. One is called P channel, other is S, and they are related by the quantum Raka matrices. And here Murray and Seiberg, they did braiding operators and find out the exact braiding eigenvalue. So you can compute basically this theory from the 2-dimensional transfer. So and yeah, though the quantum Raka matrices is basically, if you know this ST2 algebra, there are notion of the Q deformed version. So classical to promote a quantum number, and if you substitute Q tend to 1, you will get a classical ST2 algebra. So Raka matrix is nothing but it is like a three particle fusion. One can understand. There are two ways to do this tensor product decomposition. So you'll get this SU2 Raka matrix. So this SU2 Raka matrix is well known. I think the coefficient is exactly computed for any arbitrary color by Kirlo and Vestiken. And for higher rank, there are certain Raka matrix is known. So for that, one can compute the invariant exactly. So yeah, to fix on, so earlier we thought that any knot can be redrawn as a closure of 4-strand grid. So, but this is not true. And so for that, one need to define more than 2s2 boundary, 3s2, and one can generalize n-s2 boundary with a 4 puncture. And then one can add here braiding operator B1, B2, and make other knot and whatever the construction. And do whatever the complicated diagram, one can compute the invariant. And this is just simple example. If you operate, just say this is a vacuum state and add this braiding operator, and you will get the Chern-Simons invariant. If you in the terms of the ST2, this is the Raka matrices and braiding eigenvalue, you can substitute the Raka matrix given a representation, and you will get the well-known polynomials for any representation of. You can see this is the polynomial and the coefficient is always integer. Yeah. So here, this is already studied from last 2 decades. So now the main problem is comes the mutant knot, and the mutation is take a 2 triangle and do the 180-degree rotation and fit it back. This operation called mutation. And this two knot is a distinct knot. And let's say if you compute the well-known Jones polynomial, Kaufman, any polynomial, they will get the same result. Even if you do, if you take the SU2 and put arbitrary any representation, you will get the same polynomial. So,
sorry, could you say again? What's the definition of the mutation? How does it work?
yeah. So this is, let's say, rectangle. So it's braiding, and there are two legs in and two legs out, and do 180-degree rotation, or even you can do from x-axis or y-axis. The third one is actually not independent. You can do this path and mz equal to mx and my. So these operations called a mutation. And
Do you just cut, rotate, and
yeah, flip it back.
did you mirror it as well? You rotate and flip it?
Yes, so take this rectangle and rotate by 180-degree and flip it back. So you can do a two-way. One is like a horizontal. If you have axis, like you can put a mirror here, or you can do the x-axis rotation and flip it back. So these operations called a mutation, and any well-known polynomial cannot distinguish this knot. So in yeah, so in 1994,
Excuse me.
yeah.
So you're saying that just those three polynomials cannot distinguish those knots, or there's just no group, no representation whatsoever?
No. I'm coming on that point. So in 1994, yeah, in the Chern-Simons theory framework, they studied this knot for any arbitrary representation and claim that it cannot be studied. Mutation cannot for any arbitrary representation, but there is one loophole. So they missed something which we have studied. So, and on the other hand, there are famous knot theorists, Morton and Cromwell. So they used some different method. It's called satellite and cabling method, and they claim that this SL4. And if you take the mixed representation, they do distinguish the mutation. And what is the main point of taking the mixed representation? Because if you do the tensor decomposition, you will get a multiplicity, and that's play a crucial role. And here they discuss about in the Chern-Simons framework, they take this kind of accountment, but there are certain things they overcount. So that's why they claim that it cannot be distinguished. So
Sorry, say again. What's the issue with the multiplicity? Which multiplicity?
it took a more. So this is presentation. But yeah, and this method in the math side, the method is very if you want to compute, because here this knot which I just showed you. If you draw as a closure of closure of braid group, so it's a 12 strand braid, and the number of the bases they take is like 12 factorial. So it's very difficult at those times to compute at least the higher the invariant. It's roughly took 2 days to get the SL4 invariant because yeah. So yeah, so Chern-Simons theory can detect mutation. Yes, so in 2014, 15, the first Wigner 6J symbol, that's Raka matrix, it's studied by Gu and Joker in 2014. So here the crucial thing is if you do the tensor decomposition, so the conformal blocks, you will get the multiplicity. And if you take any symmetric or anti-symmetric representation, and if you do the tensor product decomposition, you will not get any multiplicity. And that's why it's play a crucial role to detect the mutation. And so we have to label by this conformal block as a multiplicity. So R4, R3 is a multiplicity label. And so, yeah, again, because these knots, this Wigner 6J is known only for the 4-point conformal block. So if you want to study this kind of knot, you have to redraw this knot as a 4-puncture boundary. So for that, we need this kind of state. So higher multiple S2 boundary state. So we have defined this, generalized this state in the Wu and Joker papers for n boundary state. So suppose if we have a NS2 boundary and with a 4 puncture, this is the general state. We have checked all the consistency. You can add here loop state and go on the lower dimensional state. So this we have checked all the things, and now then we have computed this state. So this operation is commutation if you do the 180-degree rotation, and we saw that there are some phase factor coming. And if there is no multiplicity, these two states are equivalent. So that's the reason we get the exact derivation of this mutant knot. And so actually this took 2 months to redraw this diagram because to 4 puncture, there are some horizontal loop which you can make a 3 boundary and 4 boundary and so on. So that take a lot of time, and we have computed this one, SLN invariant, not 4. And you can see if you put A equal to Q, A is Q to the power N. So if you put N equal to 3, this is 0. N equal to 4, they do distinguish. And this is exactly matching with the node which by the Murakami in it is roughly took 2 days to get this invariant. And this Chern-Simons theory, because we have only the this Raka matrix is 10 dimensional, so 10 cross 10. Sorry, it takes roughly 15 minutes to compute the SLN invariant. So it's very fast. And so then we have studied, because we studied the more mutant pairs in our other works, and there we found that there are certain nodes which has a universal structure in the difference, and there exists certain mutant knot which we call anti-parallel mutant knots, which even 2, 1 cannot distinguish. So we need a higher multiplicity, higher dimensional mixed representation to distinguish that. So here is the this open question. So given a mutant knot, looking the geometry, I cannot say which mixed representation can distinguish this mutation. So this is a still open problem, but mixed representation can distinguish the mutation. This is the whole picture of this, and we have listed all the new invariant in our website, not ebook. So one can find all the higher rank homological invariant of knot in this website. And it's a free access, and this invariance is very useful to validate this integrality structure predicted in the string topological string duality. So we have validate this integrality structure for 100 prime knots, which is mentioned in this paper, and there are certain applications in the multi-boundary entanglement, which is very essential. The polynomial is play a huge important role to study the multi-boundary entanglement. So basically, one can see just like example, this you have a tensor product state, and you can study the multi-boundary entanglement here, tracing the boundary and compute this information. Yeah, so there are other techniques which I was talking about. There are highest weight method. So right now we have a limitation into compute. We are restrict ourselves as a 4 puncture boundary. Suppose any knot which we cannot draw as a closure of 4 strand weight. So we are unable to compute this in the Chern-Simons framework. So there are a couple of different methods which is called a Restriction-Taylor approach. It's already known, but its modified version is given by Mirno-Morjo. So what we have to do is, like, we are not working on the tensor product state. We have to work on the irreducible representation. and that makes the computation more simpler. So at the end, we need actually the exact computation because it's very difficult if you work on this. Only the tensor product is faced. So yeah, so the home free PT, if you have arbitrary braiding A1, A2, B1, B2, so one can write a general formula. This is the home free PT. SQ is the quantum dimension of representation Q. And yeah, this R2 is related by some unitary transformation matrix. And this UQ is there are a way to compute is a highest rate method that I have just shown. There's another way to compute this invariant. And this UQ, we have found the most general formula. If suppose if you have any knot and link, often carry the arbitrary representation, symmetric representation. And we have shown that this UQ matrix is related to the SU2 Raka matrix with some change of variable. So then one can compute any colored invariant, obtain any knot and so and we have found the more general formula for this link carry it's a two-component link carry the arbitrary representation, and this is the closed form expression for the colored complexity polynomial. So yeah, of course, if you go for higher braiding, we need this involve more unitary matrix and it's very difficult to compute. So now I came to the other problem. So there is a class of knot. It's called a weaving knot. It's a it's closely related to the torus knot. Torus knot is like sigma 2, sigma 1, sigma 2, sigma 3 h power n. But here there is some alternating sign orientation. And this family has an interesting relationship. So it has an infinite. It's this complement space. So complement space is like if you remove this knot from the three manifold space, the complement manifold has a hyperbolic structure. So this family has a.
Sorry, are these weaving knots related to weaves? So I know a weave is a braid where effectively
Yes,
only
this
one.
is the weave braid word.
But how's it related to this picture? I don't recognize a weave.
So there is sigma 1, sigma 2 inverse, sigma 1, sigma 2 inverse, and so on. And this is just an example. It is a more general definition. This is the weave. So you have a sigma 1, sigma 2 inverse. And if you put a sigma 1, sigma 2, and so on, it's a torus knot. So this is very close to, and in torus knot we know everything, but here it is very known and is recently studied, and it has an interesting feature. So this knot capture a maximum volume if you compare with the same crossing knot. So that is one interesting thing to study this kind of knot because it has an interesting volume bound. And other thing is.
So which volume are we talking about?
It's octahedral volume and tetrahedral. So it's a bound given in this paper. It's this theorem, but we don't know the exact volume. For exact volume, we need to study this colored zones for this family. And numerically, one can compute their software, but if you want to study this, test this theorem or then we need to work out this. We need to compute the colored zones for this.
The volume of what?
A volume of the complement space.
So
you have a knot.
because you started with something without a metric, just topologically.
It's a topological volume. It's ideal tetrahedron. So filling with the ideal tetrahedron, the complement is. So it has some hyperbolic structure.
Yes, I think the same is the complement of knot in a free sphere.
Yes.
Carries a unique, up to rescaling, a unique hyperbolic metric of negative fixed curvature. You fix that scaling, then we have this model.
And if you do this asymptotic of this, so it is very sharp bound. So that's why we are interested to study the asymptotic of this polynomial. Still, this is not well explored, and it is not well explored. Like the torus knot is, we know everything about that, But this knot is not well, like, even if we don't know the Jones polynomial, the closed form expression, even complexity is not well known. So in 2017, Misra and Ross has studied this W3 comma n, so it's a 3-strand array, and their method is recursive, and they have computed the numerical numerical coefficient of Jones and Homplifity and Kono polynomial. And this is not a closed form expression, so to study the asymptotic. So if you know the because this we need the function of n and p. So we study the asymptotic. So so myself and right now we have it's almost done, so it will appear very soon. So what we have found using the modified RP approach, we have computed the exact coefficient of Jones, and is why it is interesting because this the coefficient of Jones, and if you sum over this, this gives you the determinant of the knot, and it's related to the Lucas number. It's a close, is a family of Fibonacci number, and if you go for higher grade, what I'm working on that. What I found that this structure is preserved, and it's like the generalized version of Lucas number, but it's still, I mean, it's very difficult, like to the trace. It's difficult to compute this trace because it's a 2-dimensional matrix. It's the power n. It's difficult to evaluate, but this has many interesting features to study this. So yeah, and then we have computed for the generalized version of leading knot and this paper and the quasi-alternating knot. It is like you have to do the twist, and here in the braid work, and you'll get the different class of knot. So we have studied in this paper in the colored home PPD polynomial, but still we don't have a closed form structure here. It's like for any color, if you want, I can compute. I can compute the invariant, but what we want is a closed form to study the asymptotic behavior, and that gives actually the volume information. So right now, I mean, still it's the open problem, and so if we have this color closed form expression, then we can address this volume conjecture. Yeah, so there are recent development in non-keyword correspond by Kucharski, Marcos, and Mark Stosik and Sokowski. So I'm going to just a brief introduction of this not keyword correspondent. So it means that the not keyword correspondence is that any knot where associates some keyword. So keyword is represented by some finite set of nodes, and this map is basically this nodes associate with some complex vector space, and there are linear maps between them. This is from math side. Any colored complexity polynomial can be rewrite in the most general form. And if you see in the denominator part is a cubo comma, is a fixed quantity. And one can find out what is M, and Cij is a Quivers charge matrix. And the other and the interesting thing is this Quivers matrix does not depend upon the rank of the gauge group. Suppose if you have a Jones polynomial and you can construct the Quivers, and the other variable a, and in the Kono polynomial we have a t. It's a linear in di. So di is the dimension of complex vector space, and so as an example, I showed that you have a trefoil, and one can rewrite into this form. So this is still a tedious task. So right now, what we are focusing, and also I was discussed with Sokowski during my postdoc. So right now, he's a PhD student, and we are working on that. There are interesting property of this Quivers. This diagonal entry is the degree of reduced Kono polynomial, and there are some off diagonal entry that you can compute if you know this one. So right now, what we are going to do, what we are doing is this. So if you know this, because this is already known, you can compute the Cohen polynomial, and knowing this information, and there are some set of differential operator, one can perform with this coefficient and extract this. So we have defined a method that one can compute this colored super polynomial. This is called a super polynomial, and it's a 3 variable, triply graded, and just knowing the simple uncolored, just a fundamental representation. And this is more powerful. And we don't need to go to compute all this stuff. It's very tedious job. If you know this, and one can compute this all. If you know this and just plug it, this is the most general structure. So this we are right now doing, and there is another word parallel. So this is a double twist knot. It's the infinite family, and we have computed the most general structure of this Quivers, and the Quivers matrix is 2m cross 2m. The size is 4mp plus 1. This is the size of Quivers matrix, and yeah, the elements ui. This is a block diagonal elements. Its size is 2m cross 2m, and we have give the exact expression of this for generic class of this double twist knot. So there are many more to explore. So this area knot theory is like, it's a bridge of math and physics both. So recently there are lots of work going on this entanglement and Quivers, and there are many more things going on. So currently I'm looking at this aspect of. Okay.
Great, thank you very much. Okay, so the quiver, how did you get it from the knot? Are you brushing it? What's the process?
Quivers is coming from the basic idea. There are the home PT is a generator of O-graph of a partition function in the topological string. You can express into the product form, and there are similar expression exists in the Donaldson-Thomas invariant is a math side. So that is generated by some kind of Mottwig generating series, and they compare this exactly, and this is very strange, but it is exactly the form is this, and they have mapped with this. This is a generating series of a partition function as a home PT. And this is for symmetric color. And the other side you have a Quivers theory. So and they compare and claim that this is the most general structure. Even one can put a T, the additional is also linear. And yeah, so this is and this is proven for Arboretum class of knot. Any Arboretum knot has this structure. It is proven by Paul, Wedrich, and so on. So right now, I mean, yeah, still there are lots of work going on.
So what is A here in this formula?
A is the additional variable q to the power n.
So Q?
Oh, this A is the same A. See? It's the second variable.
Capital A is Q to the power n.
Yeah, it's the second variable. Home flip it.
So can I continue the question? What does the quiver do for us? We got the quiver, then what's the consequence?
Yes, it's still a physical consequence. We don't know. It's still there are the claim that there are some class of supersymmetric quantum mechanics behind that, but still it's not well explored. But there are lots of application in the string theory picture. But it's still, yeah, there are more things going on in this direction. So what we are trying to study is like also the Sapolsky thought that like doing this exercise is very difficult. If you can understand from just knowing simple colored super polynomial and uncolored super polynomial, and can we build the Quivers. So this is the main task which I'm interested in. And there are lots of application in other direction.
But also mathematically, would it simplify things because now you can do combinatorial things perhaps using the quiver?
Yeah. Other side, I think it is related to the Donaldson-Thomas invariant, and that is proven it is integer. And this side we have a reformulated LMOV integer or the BPS state. And this is not, this is, I think, is proven into integer, but this is one way to cross check. If we can write the BPS state in the terms of a Donaldson-Thomas invariant, it's one way to say this is always the integer. This is one way to prove that. But yeah, there are connections to the math side, but I'm not exploring that area. But yeah.
Okay, that's interesting. Any other questions? Vivek?
Sorry, I have a vague question. At the end, the list of results you had, how did the beginning of the talk factor into this? Was there the issue with the multiplicities? I didn't quite recognize.
Here it is only symmetric representation because this is only for symmetry. It's not carry the information on this. Still, this is an open problem. If suppose if you have a multiplicity here, the more general representation, what is the Quivers? It's not known. So this is only for asymmetric, because the Ogre-Buffer partition function is there for symmetric representation. They have this connection, but if you have a more general, it's not. There is no mix.
Any other questions? Okay, if not, let's thank Vivek again. Very nice talk. Yeah, thank you, everyone.